Okay, so we're going to go ahead now and take a look at example number 1. So we just defined what a alternating series was, and here we're going to take a look at the alternating series we started with. This is a 1 minus a half plus a third minus a fourth and so on. And oftentimes you'll hear me refer to this as the alternating harmonic series, because notice it's all the same numbers from the harmonic series, they're just now being added or subtracted. So using the notation that we just kind of mentioned up above, one of the first questions I'm going to ask here about this alternating series is, what is the a sub n? Because I can kind of see again that every formula on the inside of that series notation should be able to be expressed, if it's alternating, as -1 to a power, and that should be multiplied by something. Well, here, yeah, you might be able to see that it looks like I have -1 to the power, and if I was kind of able to like imagine removing that, what I would be left with is a 1 over n. So here, I have an a sub n that's the same as 1 over n. Okay? That's the piece once I've separated off that -1 to the power. So this is going to be an important thing to consider, because here in example 1, again, our goal is to see how could I take an alternating series and determine if it converges or diverges. Okay, so I'm going to ask here a whole bunch of different kind of true-false questions and some smaller bits and pieces to help work up to a conclusion. And then we'll summarize all this in a nice theorem. So here's my first question, true or false? And I'd ask you to think about it. A sub n plus 1, the number in spot n plus 1, is going to be smaller than or the same size as the number in spot n, as a sub n, for all n. And for the moment, just completely ignore the and portion. Just take a look at that and see if you would agree or disagree. Well, hopefully you would agree with that statement, because notice that whenever I plug in a bigger number into a sub n versus a number that's earlier, so if I plug in something like a 3 versus plugging in a 1, I definitely am getting a smaller number. Notice that this here is an indication that my sequence is decreasing. And notice here I am saying a sequence because by itself, a sub n is just a sequence. It's not until I put this a sub n into a series that I end up, or into an addition problem that I end up with a series. So I can see here that, yeah, this seems to definitely be decreasing. That's not a problem. And when I look at the other criteria, the limit approaching 0, well, that also seems just painfully obvious that that would be true. So it seems like both these statements are true. The weird thing is that if both these statements are true, I can start to reach a lot of other interesting conclusions. So let's take a look down here at part C. I want to compute the first, second, third, fourth, fifth, and sixth partial sums of the series. Now, in case you've forgotten what that is, remember that when we say partial sums, that means we're going to be attempting to find S number 1, we're going to be attempting to find S number 2, S number 3, S number 4, S number 5, and S number 6. And I'm going to intentionally lay them out on the page in these locations. Now, remember that these partial sums are just going to be telling us how many of the terms of this sequence we want to add together. So if I'm dealing with 1 over n, S number 1 would be really, really easy. That's just the value 1. Whereas S number 2 is supposed to be 1 minus a half. And of course, that should turn into a 1/2. And so I want to go down and do this for each one of these individual values. And so I'd ask you to try to go ahead and fill these out on your own. Of course, I'll go ahead and quickly write down what I get for each of them. So if you need to pause the video to double check all my numbers and make sure that you feel confident with the results, please do so. But I'm just going to quickly go ahead and jot this down. Okay, so I have all of my different partial sums written out here up through partial sum number 6. And I'm kind of interested in the way that I've laid these out on the page. What you'll notice is that I've kind of separated out into these different columns odd partial sums, s's that have an odd number on them, and s's that have an even number on them, so our even partial sums. And I'm going to kind of separate these right now into some different colored groups. I'm going to have a red group, which is the odd stuff, and I'm going to have a blue group, which is the even stuff. And the interesting thing here is obviously these lists are not finite. I could definitely keep these lists going if I found like S number 7 and S number 8 and S number 9 and S number 10. I could keep building to these. But the true-false questions that I'm going to start to ask on the next page are going to deal with each of these respective lists. Take a look here at part D. The even partial sums, that is the blue guys, the even partial sums for this series form an increasing sequence. Okay, so I can see that these guys here in blue are definitely going to form a sequence. They can create a list of values. And the question is, are they increasing? And how would I know that? Well, if I look at the values so far, let's see, I go from 1/2 to 7/12. Well, that's definitely an increase because 1/2 is the same as 6/12. So if I go from 6/12 to 7/12, that's an increase. I can also double check maybe with the use of a calculator that 37 over 60 is bigger than 7 over 12. So far it looks to be increasing, but how would I know that it's always increasing? Well, here's what I'm going to go ahead and argue. I'll say this. We note that for k greater than or equal to 1, let's suppose I had an s sub 2k. So notice k is just going to be some variable. It's going to tell me which number in the blue list I'm working on, but that's going to correspond to an even partial sum. So I wrote that as double the value of k. Notice then if k is a 1 or a 2 or a 3 or a 4, I always get an even number down there on that index. Now, I could write out what this actually looks like, because I know this is the addition of the first 2k items out of the addition problem. So I'm going to go ahead and start to actually write this in the following way. This would be a number 1 minus whatever a number 2 is, plus a number 3 minus a number 4, and I would kind of just keep going and going and going until I finally got to a number 2k minus 1, and then I would finally subtract off that last item. Notice again that all the even things are what are going to be subtracted, and it's the odd numbered things that are positive. So this is at least what I have. But the cool thing is I can start to go ahead and add something to this picture. I'm going to go ahead and add in some parentheses. Notice that when I do this, I'm not changing the sign on any of my values, but I'm kind of buddying up each of these, or each of my numbers here with some other value. And again, the goal is to figure out if this is increasing. That is, if I added kind of one more, if I increased k by 1, and so I went up another 2 items, right? So like if I go from S4 to S6, I have to add 2 more items into the addition problem. If I add another parenthesis pair at the back, would I get an increase, or would I get a decrease, or would it stay the same? Like, how would I know? Well, this is where some of our opening facts become really important. Remember, we had said at the beginning that our a sub n sequence was decreasing. That was our first true-false question. And so now if I take a look here, I can ask, look at these sets of parentheses. What number's bigger, the number in spot 1 or the number in spot 2? And keep in mind, that, again, a sub n is just the sequence 1 over n. Well, it seems like here that the number in spot 1 is definitely larger than the spot, or the number in spot 2. So that means that this set of parentheses is a positive amount. What about the next set of parentheses? What's bigger, thing 3 or thing 4? Well, yeah, definitely thing 3. So this is a positive result. And in fact, we can then say that since a sub n plus 1 is less than or equal to a sub n for all n, we know that each, and I'll just write it like this, right? Each parenthesis is positive. So that would definitely mean that if I continued to add on more sets of parentheses, that green S sub 2k is going to continue to get larger the bigger I continue to make k. So then clearly S sub 2k is increasing. Okay, so I could go here and I could actually mark true on this statement. It seems again like every time I go up to like S number 8, I'd have to add on 2 more things, the 1/7, the 1/8, and that's like another parenthesis pair, and that's positive, ultimately positive stuff. So it is increasing. Great, okay. I'm not really sure why that matters at the moment or how this helps me get to showing that this alternating series converges or diverges, but it seems like it's definitely true. All right, so let's take a look here at part E. The sequence of even partial sums for this series is bounded above by 1. Okay, so I'm still talking about this same list of values, but I now want to know if it's bounded. Okay, so well, let's see what we got. Maybe I'll write this again. We note for k greater than or equal to 1, I'm going to go ahead and start to write out the sum of the first 2k items again. Okay, so here's what I'm going to have. I'm going to have a number 1 minus a number 2 plus a number 3 minus a number 4. And then I'm going to do plus a number 5, and then, I'll do a dot, dot, dot here. And then I'll kind of have at the very end, I'm going to have a, let's see, how about a minus a sub 2k minus 2, and then an a sub 2k minus 1, and then an a 2k. Okay, now this looks a little different than how I wrote out the terms last time in the part above, but you'll notice that it is actually all the same terms. I've just kind of written a couple extra. I've written out a5, and I wrote one extra term that came before the a sub 2k minus 1, which of course would be a sub 2k minus 2. Again, all the even numbered things are being subtracted, and all the odd numbered things are being added. Now the reason I'm going to do this again is I'm going to attempt to introduce some new parentheses. Notice, though, how I'm going to attempt to introduce them. I'm going to attempt to introduce parentheses right here. I'm going to put the A2 and the A3 in a buddy system, A4 and A5, and then after that dot, 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 I'll have the A 2k minus 2, the A 2k minus 1, and then finally our A 2k sitting at the back. Now, I've left off a lot of the signs, like the pluses and minuses here, because I got to be careful in the way that I write this. Notice I can't just put parentheses around this A2 and A3 and not have anything change, because I have a negative out front. But I'm going to imagine that I factor the negative out from this. If I put a negative out here, notice I'm going to have to change that plus sign that used to be in the middle to a minus. Double check really quickly that if you redistribute, you get exactly back to where we started. That would mean over here, I get the exact same sort of behavior. At the back, I get the same sort of behavior. Notice that everything's been buddied up again, except I've kind of left A1 alone, but I've also left A sub 2k alone. Everything else can get buddied up. But now I can go ahead and I can start to see the exact same sort of interesting conclusion I can draw about each set of parentheses. Take a look at the first set of parentheses. What number's bigger, A2 or A3? Keep in mind, A sub n is 1 over n. Well, definitely A2 is bigger, right? Because we already said that the bigger the n you plug in, the smaller the result. So each parenthesis is a positive number, a positive number. And definitely we said that all the things in this list already are always positive. So notice that this is just whatever A1 is minus a number that's positive, minus a number that's positive, minus a number that's positive, minus a number that's positive. And the more things that are in this addition problem here, the longer this partial sum goes on, the more stuff I end up subtracting. So I'm going to go ahead and write this. I can say, since a sub n plus 1 is less than or equal to a sub n for all n, we know each parenthesis is positive again. So then I could definitely argue here that s sub 2k, which is equal to everything that we had up above, isn't it definitely going to be less than or the same as just whatever A1 is. Because right now, if I have a bunch of things that are being subtracted, then it would definitely be bigger if I didn't subtract. So here I just have A1 with no subtractions, whereas S sub 2k is A1 with a bunch of subtractions. So this is definitely true. But of course, if AN is the same thing as 1 over n, then A number 1 is just 1. And so then automatically, by definition, I can see that S sub 2k is bounded above by 1, right? S sub 2k is definitely less than or equal to 1 in all moments. This is also true. So these are some really interesting ideas. We've been able to show that the even partial sums are increasing, and the even partial sums are bounded above by 1. This seems interesting. So here's my question. It's similar to part F, but not exactly what part F states. What would you conclude about the sequence of these blue values? What would you conclude about S sub 2k if we know that it's increasing and we know that it's bounded above by 1? Well, you might be able to think to yourself, wait a minute, that sounds pretty familiar. That sounds like an idea that we've talked about before. And so we can actually say this. By the monotone sequence theorem, S sub 2k must converge. So that's really powerful. If this must converge, then that means that when I do the limit of this guy, as say k goes off to infinity, I get some number back. Let's say for the sake of argument, the number I get back is big capital S. Okay, that's the value that I get. Notice I still haven't answered the original question, which is, do you think the entire series is convergent or divergent? Just because I know, again, that this list of blue numbers is headed somewhere, it converges, doesn't really tell me anything about the entire addition problem. But I can go ahead and consider the following. Oops, scrolled too far. Maybe I could say this. Well, let's then think about what's going to happen with this red list of numbers. That would be an S, but not of just a 2k, because here if I plug in k as like a 1 or a 2 or a 3 or a 4, I'm going to end up with values that don't really seem to be odd numbers. So what I could do here is I could say, what if I made this a -1? Then notice that when I go ahead and I actually work with, I can do +1. It kind of depends on where I guess you're imagining starting. If I started here with k as a 0, then I could imagine that I have item 1, or S number 1. When k goes to a 1, I'll have S number 3. When k to 2, I'll have S number 5. And if I was to take a look at this, I could actually consider that this would then represent like the red partial sums. In fact, I'm even going to underline this in red while underlining this one up here in blue. Now, if I wanted to evaluate this, there's something really cool I could do to help me. One thing that I could note is that if I wanted to add up this red stuff, that is the sum of the first 2k plus 1 items, couldn't I do that by adding up the first 2k items, and then I only have one more item to add? But the last item that I need to add would be the number a sub 2k plus 1. Right? So again, this is A1 plus A2 plus A3 plus A4 all the way up to A2k. And this is, well, just the very last item in the addition problem. So if I was to separate this like this, notice that this becomes super easy to work with, because this is the same thing as the limit of S sub 2k. And I know that the number in spot 2k plus 1 looks like this, because, again, my sequence was just 1 over n. So now I can do the limit of both of these pieces individually, because I know that both of them actually exist. Notice that means that the first one is going to be s, and the last piece is going to be 0, which gives me a grand total of s. So interestingly, I can find that not only do the even partial sums approach S, but the odd partial sums approach S. That's really, really powerful. And so I can then make the conclusion of the following. I can say, since both the even and odd partial sums approach S, then we could say that the limit of just S sub n, for adding like n things together, must also approach S, right? Like both these things are going towards the same spot, so it's all going towards the same spot. And thus, the series is convergent by definition. Remember that if the sequence of partial sums adds up or heads somewhere, has a limit, then that's actually the sum of the series. So this is a really long, complicated argument to ultimately arrive at, I can conclude that this series converges. So all of this is really going to be able to help us create what we would refer to as the alternating series test. Here's what we have. This will kind of summarize everything we just went through. If I have an alternating series of the form looking something like this, again, the power on the -1 doesn't really matter as long as it forces it to alternate. But as long as I have a sub n being of something positive, and as long as a sub n satisfies the two following conditions, condition 1, I need to have a sub n plus 1 be less than a sub n for all n. We kind of saw that up above. We use that a lot. If I have that as true, and I also have the limit as n approaches infinity of a sub n is equal to 0, which notice we kind of used right up here when we did the limit of this last term. It was important that that turned into 0, or I wouldn't have been able to get a final answer of S. And if both those things are true, then I could kind of always repeat the above argument and conclude the series is convergent. So this is really, really powerful. Essentially, it says if you got an alternating series and you can just confirm for me these two things, we automatically know what the argument's going to look like, so there's no reason to write the whole thing. We can just immediately jump to the conclusion. We know we get convergent. So this is really, really, really powerful here. Okay. In the next video, we're going to start to take a look at some of the different examples that we could have for questions like this and see times when the alternating series works and other times maybe when the alternating series doesn't work.